Alright, stop. Let's kick it. Ice, ice, baby. Ice, ice, baby. Big questions we're trying to answer with this lesson. What actually is voltage? What unit do we measure voltage in? What are analogies of what voltage is like? What are some examples of voltages of things that we are familiar with? Now, if you're listening to this tune, you might at first thought it was Vanilla Ice. Ice, ice, baby. But it is not. Pressure. Under pressure. The lyrics of the song say under pressure. So that's the big thing that I want you to get from this video is, well, what is voltage? What actually is voltage? So what I want you to remember is voltage is basically like pressure. It's like electrical pressure. Let's look at our official definition. Voltage, the electrical pressure or potential electric energy between 2 points. So if we think about that, if we have 2 points, what that's saying is like the potential electric energy. It's like saying if you have a point here and here, how bad does that energy want to go from, let's say it's starting here, how bad does it want to get to here? It's like, how bad does it want to go? Let's first answer, what unit do we measure voltage in? This one is pretty simple. We measure voltage in volts. The way that we would type like a number for voltage, let's say something is 12 volts. We type in 12 and then we put a V next to it. Let's say something is 1.5 volts, 1.5 volts. So that is how we would write voltage. We just put a V next to the number. Let's move on. Let's try and figure out a little bit more now what actually voltage is. And we said electrical pressure, potential energy between 2 points. If we think of a hill, so if we think of a hill here, this hill is obviously smaller, and then this hill is obviously way bigger, and we can see some people there for scale, and you can tell it's way bigger. So if we think about 2 points, so on that smaller hill, the 2 points from the top to bottom, smaller. If we go to the big hill, those points from top to bottom are bigger. So let's say we had a ball, and we put a ball at the top and of each hill, and then we let that ball roll down. It's kind of like, which ball would have more energy? Would the ball have more energy at the low hill rolling down or the big hill rolling down? So obviously the ball will have more energy when it's rolling down the big hill. Because if you think about potential energy, it has more opportunity for gravity to accelerate it. There's a bigger difference between the points. It's like almost like that ball wants to get down the hill even worse than even more than it does on the smaller hill. So it really would have way more energy going down that big hill than it would the small hill. Let's look at another analogy. So if we think of some balloons, if we look at this balloon here, this one, there's just a little bit of air in there. It's almost completely deflated. And now here's what I want you to try and imagine. I want you to imagine the air molecules are like the electrons. So in a way, let's kind of think of this, it's kind of like a battery. In a way, you can kind of think that. So that the air molecules would be the electrons. Now in this one, the rubber, so the container of the balloon, it's not exerting a lot of pressure on that air to get out of there. The air is kind of even with its surrounding in terms of the pressure. So there's not really much momentum or much force or much really energy to push air out of here. It's just kind of equal. Now if we go on this balloon, so this balloon is blown up and it's tied off. And what's happening is that rubber got stretched out. And that what that wants to do is now it's like compressing, it's pushing. There's more air inside of this balloon than there is on the outside. So it's like if we pretend those are electrons, it's like those electrons, they want to get out of there. There's pressure. So when we were saying like that song, under pressure. So I want you to again remember pressure. So there's pressure here for wanting to get those electrons out of there. It's like these electrons, they want to escape. They want to even out. Like we kind of talked about in one of the other lessons, diffusion and osmosis, kind of similar to those aspects again, is that the air pressure in here wants to be the same as outside. So those electrons want to escape. They really want to get out of there. Now if we think of this balloon, now we think about, so there's a flame under it, and then there's a llama corn. A llama corn is a combination of a llama and a unicorn, if you didn't know. And the llama corn is sitting on top of that balloon. Let's say that llama corn weighs, let's say 100 pounds. So there's flame under here that's heating up the balloon, and then there's a llama corn sitting on top of the balloon. So now here's what I want you to think about. Which one of these, just think about the air molecules. Between these two balloons, which one do the air molecules want to get out of, like, worse? Which one of these do the air molecules want to get out of more? So the air molecules definitely want to get out of this balloon more, because now that flame, it's like heating up and exciting the atoms even more. So now there's even more pressure because they're bouncing around and causing the balloon to stretch even more. And then the llama corn is sitting on top of the balloon, and that's putting even more pressure. So this balloon is under pressure, and those air molecules are just wanting to escape really bad. So this would be like a higher voltage. This would be less voltage than this. And this would be basically like no voltage. Like the air, like I said before, the air molecules don't even care about getting out. They're not too worried about that. This is a very famous picture in electronics and trying to understand electricity. Your job is to be very responsible. It's okay to giggle a little bit about it because it does look kind of funny, but we need, of course, be very appropriate in how we're thinking about this. So we have Mr. Volt here is kicking Mr. Amp. He's trying to kick Mr. Amp through this. Let's pretend this is a pipe or a wire. And then Mr. Ohm is like squeezing that wire closed. So Mr. Amp is having a tough time to get through. So what Mr. Amp is doing is he's exerting pressure. He's like kicking, like punching, kicking, like get out of here, Mr. Amp, and like pushing. So the harder Mr. Amp is like kicking him through, so then Mr. Amp will be more likely to get through. If Mr. Volt is not pushing very hard, then Mr. Amp is not going to get through. So we're going to talk about Mr. Ohm and Mr. Amp in some following lessons, but what I want you to think about, again, is voltage. Voltage is pressure. It's electric pressure, really trying to push, like how much force is there pushing those electrons through. So now here's two analogies for you. And you're going to have to decide which one do you think better represents higher voltage. So we have a pressure washer here, and let's pretend the water are the electrons. The electrons are wanting to get out. So what this pressure washer is doing is it's motorized. It's a motorized pump, and it's pumping the water, and it's creating a higher pressure. So this water then comes out like a pretty intense spray, which then you can use to clean your car or the ground or whatever. And then we have this other example here. So this girl, she's holding like a sprinkler can, and then she's tipping it, and water's coming out. And for this one, what's bringing the water out is gravity. So we have two differences here. This one, there's like a pump. It's pumping the water, like pumping the water to force it out. Whereas for this one, gravity is what's bringing the water out. So look at the different answers and try and figure out which one better represents a higher voltage. For which one of these do those water molecules, so again, we're pretending the water molecules are the electrons. Which one of these are the electrons wanting to come out more? So for this one is just gravity. Gravity is just pulling the water out. So with this one, there's not nearly as much pressure. There's not nearly as much motivation. These water droplets, and again, we're going to pretend those are electrons. These water droplets they don't care as much about getting out as these water molecules do. These are like being forced out, like pushed, like hardcore getting out of there. This pump, it's like, I don't know if it's 1,000 PSI or what, but like these pumps are really pushing that water out really hard. So if you were to stick your thumb like right in front of that pressure washer, don't do it. It would like leave a blister on your thumb because that's how hard that water is coming out. Whereas this, with the sprinkler can, you put your thumb on there, well, that's just coming out nice and easy. So this water is definitely under higher pressure and like would represent an example of electrons really wanting to get out. Let's do a couple more comparisons. Right here, here's a AAA battery. We've seen a lot of these before, like in remotes and so on. And then here would be a D battery. So it's obviously a lot bigger. The D battery would be in like maybe old style, like flashlights, maybe some old style toys, all kinds of different things. So between the two of these, So this is 1.5 volts. I want you to take a guess. How many volts do you think the D battery is? So if the AAA is 1.5, how many volts do you think this battery is, the D battery? So now both are actually 1.5 volts, believe it or not. So just because this is bigger doesn't mean it has more voltage. So both of the atoms in here, the electrons in here are under the same amount of pressure of wanting to get out. But this battery will just last longer. So now if we look at, we got this like square-shaped battery, which you've seen before. This is a 9-volt battery. So how many volts do you think this battery is? So if this is 1.5, how many volts do you think the 9-volt battery is? So I basically gave you the answer, and the answer is already the name of the battery. It's called a 9-volt battery, so this is 9 volts. So if you think about this, this is 1.5, this is 9. That's pretty interesting. This is quite a bit more volts than this. So the chemistry inside of here, again, so it's not the size, it's the chemistry inside of here that's what's creating that electrical charge, that pressure. It's like the electrons in this battery really, really want to get out and escape way worse than they do in this one. Here's some examples of voltages of common things that might be common to us. So for example, a AAA battery, AA battery, these generally these round batteries are 1.5 volts. And then if you think about like a cell phone battery, a lot of these like kind of smaller handheld electronics use like a 3.7 volt battery. Then we have our 9-volt battery, which we use in a lot of different things like smoke detectors and so on. We go to cars. A car battery is 12 volts. The socket at your house, that's going to put out 110 volts. And this is AC current versus this is DC current. So AC means alternating current, DC means direct current. We'll get into that at a different time. So a lot of your household items, they take in that 110 volts, and then a lot of them convert it to a voltage more so what it then would use. But this is 110 volts. And then a lot of houses have another type of like wall socket, and that would be 240 volt or 220 volt. And what that's doing is basically doubling this. So like dryers, air compressors, some of these like big electric motor type of things that need that extra voltage use that 240 volts. And then let's get crazy. These power lines are like 115,000 volts. That's what's going through here. So at this point, I hope you feel way more confident about what voltage is.